Okay,
Great.
so yes, so I'm going to talk about NISAR mission. This is a presentation that Paul Rosen gave at the IGAR's International Geoscience and Remote Sensing Society meeting last July in Pasadena with a few updates. So it's a brief introduction to the NISAR mission. NISAR is going to be a global mapping mission with the big advantages of radar that Josh just described. It's all weather, day and night, and we're going to be acquiring data every 12 days over all land all the time. Um, a- and because we're going to be controlling the orbit of the NISAR satellite, it's going to be possible to do interferometric measurements everywhere all the time. So that's the surface deformation and change component. Um, with it's also going to be using both for most of the Earth. It's going to be using dual polarization. So it's going to have the HH polarization and the cross pole HV polarization. So that's going to be enabling the global biomass measurements shown in this upper left part of the right-hand applications scene. Uh, the interferometric measurements are going to be used for global ice dynamics, especially on the ice sheets of Greenland and Antarctica. And the INSAR will also be used for things like earthquakes, earthquake deformation, deformation due to aquifers, groundwater. And then there's the agricultural mapping and soil moisture. So the NISAR instrument has the radar part was this upper part that happens to have this gold colored foil. It's not foil, it's a insulation. Um, that was built at JPL with all the radar transmitters and both S-band and L-band. Then that radar instrument was connected to the core satellite built by ISRO in India, which has this blue insulation material. So the two parts of the satellite system have been connected together there in India, and they've been undergoing the last tests, and they're on track for launch presently planned around the end of March or early April of this year. So the key thing will be obviously when the launch takes place. We don't know the exact date yet. That's up to ISRO and their rocket launch system. It will be launched from India, from the Indian site on the east coast of India. And then we expect to go through the initial um, calibration and validation calibration phase or commissioning, and then start getting images around 2 to 3 months after the radar satellite is launched. We then plan to go into full science operations 3 months after launch. So if it's launched at the end of March, that would be June, uh, the end of June. Uh, and then the data will be immediately available to the public online through the ASF. There's no delayed data availability. The data won't be completely calibrated when it's first released. So it will be in a preliminary status, but we're making the data available immediately to give it to the public for their use as soon as possible. And so as Joshua mentioned, the NISAR actually has two different radar wavelengths. The L-band radar wavelength was built by JPL, and the S-band radar system was built by ISRO. ISRO engineers came to JPL to integrate all the S-band radar electronics into that radar structure. And then the radar structure was shipped to India for integration with the radar satellite. So it's a very collaborative project to get this satellite system launched. The radar structure also has this boom that connects to a radar reflector so that the two radars can operate at the same time by using the reflector. So this is a unique system, having the two radar wavelengths on the same spacecraft operating at the same time. This is the first civilian satellite. We don't know what the military uses, but civilian satellite that will have two radar wavelengths on the same satellite. We did previously have the shuttle imaging radar system, mission C, that flew in 1994 in the space shuttle. It actually had three radar wavelengths, but of course it was only operated for the 10 days of the shuttle mission, not for any long-term mapping. So the key thing about, one of the key things about using this radar reflector is that we use this sweep SAR technique. I don't have time to get into the details of how sweep SAR works, but it gives the ability to image a swath that's 240 kilometers wide from the satellite. The incidence angle or angle from the vertical goes from 33 degrees to 47 degrees across the 240 kilometers. And it allows us to do this polarimetry. As I mentioned, most of the world is going to be in dual polarization, just an HH and HV polarization. But in some places, especially in the central United States and over India, we're going to be operating it in the quad pole, which is the full four polarizations, HH, HV, VH, and VV. That mode gives more information about the polarization, but it has some disadvantages, primarily in that it doubles the amount of data. So that will only be used in certain parts of the world. And then over some of the ice sheets, we're going to be using only a single polarization, especially over Antarctica and Greenland, to get with a higher spatial resolution. It's a 12-day repeat orbit, and with its exact repeat, so that the satellite is operated in a way to come back over the same place on the Earth within a few hundred meters. That enables the interferometric measurements all the time, everywhere. The SAR system has a number of different modes. I don't have time to go into all the different modes, but the key is that we can change the the resolution in the range direction, the across track direction, that can be between 3 meters and 10 meters, depending on the what we call the range bandwidth. So the range bandwidth is the amount of frequency spectrum that's used to acquire the image. The more frequency spectrum we use, the more resolution we get. The total amount of range frequency spectrum that NISAR is allowed to use is 80 megahertz. That gives the 3-meter resolution. In North America, we're going to be operating it at 40 megahertz. That gives 6-meter resolution. And over the rest of the world, we're going to be primarily using the 20 megahertz mode, which gives 9 or 10 meter resolution. The along track resolution is fixed by the size of the radar reflector, and that's going to be 6 meters globally. It's basically the reflector is a 12-meter dish, so the resolution is determined by half of that dish size in forming the synthetic aperture. So that gives the resolution, the along track resolution doesn't change globally. Similarly, the S-band will have different range bandwidths, but the S-band data is primarily going to be acquired over India. The NASA classifies missions into different classes. This mission is in what they call a mission class B, and that means that it's defined as a 3-year minimum mission. ISRO has a different mission classification. They classified the mission as being for 5 years, but the satellite's going to have enough fuel on board to operate for 10 years or more, as long as everything is going well. The satellite has to both repeat the orbit very accurately and control the pointing, how the satellite is oriented towards the ground. So that's important for the interferometry. As I mentioned, the repeat of the orbit is less than 500 meters. That for L-band, that's adequate for doing interferometry. And one of the big improvements of NISAR over previous L-band satellites is that it's designed to have a very high duty cycle. This means that 50% the duty cycle is how much of the orbit the satellite can be on. So on the average, the NISAR satellite can be on up to 50% of the time. And that means it can be turned on over all land, and ice all the time. Previous radar satellites have not had this very high duty cycle and had to limit their coverage for a variety of reasons. It requires, resources of the power and data downlink capacity, which has all been improved for NISAR. The S-band instrument, due to thermal limitations, it can only be operated about 10% of the orbit, and that means that the S-band data is going to be acquired only in a limited part of the Earth. It'll be on all the time over India and a few other places, including the west coast of the United States, one of our calibration sites. The other big difference of NISAR compared to other radar satellites is that we've decided to have the radar pointing to the left of the satellite track. So the satellite's going, as the satellite's going north, it's going to be looking to the west. And when it's coming back south again, it's going to be looking to the east. The other, all the other radar satellites are designed to look to the right, so that when they're, well, like for Sentinel-1, when it's going north, it's looking to the east. And when Sentinel-1 is going south, it's looking to the west. And because these orbits are all a lot at a slight angle, on the descending track, they're going slightly to the west due to the rotation of the Earth. That when you're looking to the left, then you're looking to the south. And that means that we're going to have much better coverage of Antarctica than these other satellites, and a little bit less coverage of the North Pole. So the very northernmost part of Greenland and the Arctic Ocean will not have much coverage from NISAR, and other satellites will cover that area. So that's why we are relying on Sentinel-1 for the Arctic. So this is an example of the dual frequency measurements that were made by this Shuttle Imaging Radar Mission C mission that I mentioned that flew in 1994. On the left here is a combination of L-band and C-band over wheat fields. And on the right here is L-band and C-band over trees in Malaysia. So we can see that the different radar wavelengths have different amount of backscatter depending on the size of the vegetation, whether it's trees or bushes, and whether it's, you know, banana trees or palm oil trees. And so the two different wavelengths will be better used to help separate the different types of vegetation where the two wavelengths are available. This is the map of the planned coverage. As I mentioned, the 40 megahertz mode is going to be operated over North America. This purplish color, with the dark purplish color being the quad pole or four polarizations. There's this area in the Midwest agriculture area, and also an area up here in Alaska that are going to be operated in quad pole. And then the blue color, the light green color here is the background land. There's the two different green colors are both background land on this map. 20 megahertz. This is the 20 megahertz, 6-meter resolution, dual polarization. DP is dual polarization. So that's most of the Earth. And then we have this plan to operate over urban areas where the L band is going to be switched to the 40 megahertz, the higher resolution, 6-meter resolution over cities. The system is designed to be able to switch back and forth, and and the data still be operated continuously, so we're able to turn it on and off and switch between the 20 megahertz and 40 megahertz and get higher resolution over cities in large parts of the world. This is an older version of the map. Some of this city coverage in Asia, East Asia, was changed, and not all that area will not be at 40 megahertz. And then the orange area here is where the systematic coverage of the area of India and surrounding countries, including Indonesia, where the S-band data will be acquired all the time, and the two radar wavelengths will be acquired simultaneously. There's also an area in along the coast of Antarctica where the S-band will be acquired with the L-band to better understand the sea ice. And then the dark blue or cyan color here shows areas where we're going to use that 80 megahertz single polarization mode to get the very high resolution, but with only one polarization for the areas with the very fast moving ice. This is details about the Indian coverage. The coverage over India has been determined by the Indian Space Research Organization scientists. So they've decided on a plan where they use on the ascending tracks with the radar, the satellite moving north, using the dual polarization, and on the descending tracks, it's going to switch between the dual polarization on some orbits and the quad pole on other orbits. So there'll be a little bit of heterogeneous acquisitions over India to optimize the acquisition of data over that area for a variety of purposes. So the NISAR is going to have released data of several different levels. The raw data or level 0 data is going to be available for people that want to do their own processing from the beginning. I'll talk about that a little bit more in a minute. Level 1 is the radar after the synthetic aperture has been formed. So that's now into what we call single look complex images in radar coordinates. That's level 1 products. Level 2 is where we've geocoded the data, put it into long coordinates, and that will have actually two different types of level 2, both multi-looked and single look. I'll talk about that in a minute. And then there's level 3 products. We're only doing these for global. We're not going to be doing that globally, except for the soil moisture. The rest of these products are going to be processed by the science team for small areas to validate that the data is meeting the science requirements. So that the level 3 products for soil moisture will be processed globally. We received a special extra allocation of funding from NASA to do global soil moisture mapping.
And Eric, there's a question in chat related to some of the NISAR products and availability from Andrew Johnston here at ASF. And so the question is, does science operations 3 months after launch include level 2 and level 3 products? And should we expect products like the L2 GunWs and L2 GCOVs and L3 soil moisture data to be available for download from ASF as early as July?
Yes, the level 2 products will definitely be available. I'm not sure about the level 2, 3 soil moisture products. The plan is we're going to have all the software ready to start processing those products. They won't be fully calibrated. The level 2 products don't require as much calibration as the soil moisture products. I think the soil moisture products might be delayed a little bit until they do the calibration to produce products that are usable by the public. Then there's the additional project that's called Opera. That's going to be discussed later. This is a separate project under NASA that was funded under NASA's Satellite Needs Working Group. The Satellite Needs Working Group said they wanted additional data sets, and NASA got funding from Congress to do these, and those are managed by the Opera project, which is separate from NISAR, and that produces the global surface water extent, the global disturbance product, especially disturbance for vegetation, and a deformation map product that's going to be over North America only. So all the NASA data, data is going to follow the full open data policy that NASA has had for many years. We've now released these pre-launch L-band sample data products. There's both that I'll talk about in a minute. And there's also data from the campaign that was flown a few years ago, where ISRO built an airborne radar system that was brought to the United States and flown on the NASA airplane. And it has both L-band and S-band data products acquired at the same time to provide that dual polarization, dual frequency and quad pole data format over selected sites in the United States. All that data is also fully previously available. And this great blue line here is pointing out that by the time that NISAR has completed 3 years of data acquisition, the total data volume will be about twice the size of all the previous NASA Earth Science data, the EOS DIS archive. So it's a huge effort. It's all going to be stored in Amazon Web Services because Amazon knows how to deal with large data volumes. The present plan will be producing data at the rate of the data products level 1 through 2. 0 through 2 will add up to about 75 terabytes every day once we start the full operation. So all the software is available online in GitHub. This ICE3 software is available on GitHub. This is the actual software that we're using to process the NISAR data from level 0 to level 3. The algorithms are available from that we're using for the science data products, and the science data validation is also available through this GitLab site. And then there's the training opportunities, including this one and RSET. the cloud computing facilities, including open SAR labs, will be discussed in another part or later today. So this is a photo taken last July after they first joined the two pieces of the satellite. It's now been fully tested. I think I've sent it to already to the last shake and bake. You know, they put it in a special system that shakes it and puts it into heat and cold and vacuum to test it to make sure it's going to work once it gets connected to the rocket and shaken in launch and then goes into space. So that's all ready to go. We're just waiting for the final integration with the rocket and the rocket availability for launch in 2 months. So this is to provide more information about the data products. This is a slide set that was prepared by Haresh Fatahi, who is the lead for the NISAR algorithm development, SAR algorithm development team. Paul Rosen, I think we didn't mention before, Paul Rosen is the project scientist for NISAR and the head of the science team and mission science team. So these are the different products. The level 0 is called RRSD, radar raw signal data. It's been slightly reformatted from the data that's been downlinked, and just to make it into a format that's usable for processing. But with its raw signal data, it has not been, it's not really usable in any direct way until you do the focusing. Once you do the focusing, we get the level 1 data with the range Doppler coordinates, radar coordinates, SLC, RSLC. That's the single look complex image and radar coordinates. We're also going to be producing geocoded SLCs. This is a new data product that hasn't been produced systematically by any previous mission. I'll talk a little bit about that. Then the geocoded covariance. This is it's a little bit of a funny name, covariance. It's the information about, it's the radiometrically terrain corrected product, and it includes the covariance between the radar channels. So it tells you about it includes all the polarimetric information, and it's been multi-looked. The G-coded SLCs are roughly the same resolution as the range Doppler SLCs, but all the rest of these products have been multi-looked. They're coarser resolution. The next level 2 product is the geocoded unwrapped and wrapped interferograms. This is these are actually processed in radar coordinates and then geocoded, and they'll be available. This is this is a product that people have in the past typically had to make on their own, but we're systematically going to make this available globally from NISAR. And then there's the geocoded pixel offsets. Those are only going to be systematically processed over the cryosphere, the ice sheets around the world. There's a special radar coordinates level 1 wrapped interferogram at higher resolution that's going to be over the cryosphere program areas, and unwrapped interferogram at a higher resolution over cryosphere areas. and the pixel offsets in range Doppler coordinates, also only over the cryosphere. And finally, there's the level 3 product, which is the soil moisture, which is going to be global, except over the cryosphere because there's no soil on the ice sheets. So these NASA uses this term, the algorithm theoretical basis document, that describes, or often abbreviated ATBD. This describes the algorithms that are used to process all of the data. So for each one of the products, we have an algorithm theoretical basis document that explains how that product is reduced. These were released an update to this was released last fall. There's a new version that's going to be released in a few months before launch in the next month or so. We don't expect any major changes, but there could be some small changes. The level 3 soil moisture is still going through the release system. It's more complicated. This was added by that satellite needs working group process at a later stage of the mission development, so it's a little bit behind the rest of the software development. And there's these product specification documents. You can go to the NISAR website and download these documents. So each one of the products will have a specification document and an algorithm theoretical basis document, which the algorithm theoretical basis tells you how it was produced, and then the product specification just describes the format of the data and what is in the data product. Each one of these is available on the NISAR website. So what was just recently released earlier this month is the NISAR sample data products. And these are made from the JAXA satellite called ALOS, or ALOS-1. It's the first ALOS satellite that was operated between 2007, actually early, 2007 and 2011. That satellite collected data over a large part of the world. The ALOS satellite had an L-band radar system, and the ASF now has all the ALOS raw data, and they are making that available either in a variety of forms for people that want to look at the ALOS data. But we've taken some of that ALOS data and processed it into a format, the exact same format as NISAR, to provide these sample data products. The raw signal data will be available only as the full data take. If you look carefully, each one of these strips is a data take. So some of these strips are very long. Some of these ones going down over Asia can be up to 8,000 kilometers long. I think the ones that come down across Asia and Africa. So that will be one giant file. It's not going to be cut up into pieces. So the raw data is just going to be the full strip. Other places where the data take is shorter, it'll come as the shorter strip. And that's the level 0 data. Not many people will be interested in working with that. One of the things that about the sample data set is that we're using the ALOS data. The ALOS data had had only a 70-kilometer swath and about 100-kilometer along track width. So this green area shows the ALOS scene size compared to the outer box here, which is the NISAR frame size. NISAR, all the level 1 and level 2 and level 3 products will be produced over this, over a single frame, NISAR frame, which is 240 by 240 kilometers. So this NISAR of the ALOS sample data is only about 1/20th of that area, but it has the same data format as the ALOS as the NISAR data. So the NISAR file names have a very long file name that has a lot of information. The first part being of course, the name of the satellite, the level number, level 0. There's a code here for whether it's regular production or urgent response. In this case, this is the level 0 data is the radar raw signal data, RRSD. Cycle number is how many times the satellite has done the 12-day cycle. Track number, ascending or descending, the radar mode, what this tells about what radar bandwidth and whether it's dual polarization, quad pol. There's a whole list of those modes. Tells you this acquisition start time, the acquisition end time. This is very similar to Sentinel-1. There's a extra release identifier here that tells about the version of the software that was used to produce that data product. Then there's the first letter here is what is the orbit accuracy, P for precise, M for medium. The urgent response data products are going to have the medium orbit accuracy, but there's also an option of doing these other even less accurate orbits. And then there's a product counter, which tells just in case they reprocess the same product to make sure there's a unique file name. And then there's a 1 character to tell whether it was processed at JPL or NRSC. That's the ISRO National Radar Remote Sensing Center. Oh, these arrows are wrong. Oops. So then the level 1 products are what most people are going to work with. It also this will be the first will be coming on that standard frame. The frames are always going to be in the same place, unlike the Sentinel-1 data that's been available from NISAR with these slices where the slices would not be always in the same place. NISAR frames are always going to be in the same location, so make it easier to work with. The radar range Doppler single look complex images are on a 0 Doppler grid, and they're always going to be on this predefined frame, track and frame. Depending on the mode of acquisition, the product will have different polarizations or different radar frequencies. So there's a whole specification for this. The file names are very similar, except that it's a RSLC for radar single look complex. And it has additional codes here for the, because it's now in frames, it's going to have the frame number in addition to the track number, and codes that tell about the frequency of the So this is L-band data. The L-band, one of the other things that I didn't mention earlier about NISAR is that we're going to have, for most acquisitions, both a main band and a second band, a side band, which, so a lot of the Earth is going to be in this 20 and plus 5 mode. So the first part of this is 20 megahertz. The second part is 0.5 for the second band. The two bands are used to do the ionospheric corrections. We didn't really explain about the ionospheric corrections, but having that second band is very important for doing accurate ionospheric corrections. So this part of the file name tells us about the two bandwidths or frequency spectrum content of the two bands. And then the second part here shows the polarization information. In this case, DH for HH, HV, dual polarization, H transmit. It could be DV for V transmit, but I think the normal mode in most places is DH, DH. I don't know why there's another A here. Anyway, and then the rest of this file name is the same as what we explained for the level 0 data. The sample data has been focused from the ALOS SAR data, and there, we produced two RSLC sample products and to enable interferometry. And there are two dates in 2008. 2008 October 12th and 2008 November 27th. Oh yeah, and so this is there's an extra character here. The orbit accuracy character has been moved to a separate character here. And the P in this particular, file name is for partial frame. So because this ALOS data is only a small part of the NISAR frame, it's considered a partial frame. In there will be some partial frames processed for NISAR where we've been doing that switching between different modes. So there's also going to be SLCs produced with partial frame coverage. And other ones that are processed on a full frame. The frames will be fixed, but sometimes the SLC doesn't cover the whole frame. So then there's also the geocoded SLCs. So this is still the full resolution single look complex image, but it's been geocoded. So it's all the geometric distortions have been taken out and the topographic phase has been removed. So we can, the big advantage of this kind of product is that we can you can form an interferogram by simply cross multiplying the two products and get an interferogram at full resolution with no additional processing. So this is a very new type of data that hasn't been produced systematically for other satellites, except for the Opera project that's producing. In Opera, it's called they've decided to do, they have a co-registered SLC product that's also geocoded. So it's essentially the same type of product from Sentinel data. The GSLC products have a very similar naming convention to the RSLC, so I'm not going to go through that. The key thing is that all the topographic phase has been removed from the GSLCs, so you can form an interferogram that's without the topographic phase without doing any more calculations. The geocoded GCOV, GCOV, GCOV product is a geocoded covariance. It's called covariance because it includes this covariance between the different radar wave polarization bands, polarization components. And it's so it's radiometrically terrain corrected and geocoded, and includes multiple bands for the different polarizations. And so the naming convention, so there's a sample data product from ALOS that's over the western part of the Mojave Desert in California. It's Rosamond Dry Lake. It's this dark area in here. It looks like water, but it's actually just a very smooth dry lake. Most of the time it does flood occasionally, but in this particular scene, it's just extremely smooth, so it looks like water, but it's not actually water. And the naming convention is mostly similar. It says GCO for the GCO product. It tells you about the polarization in this area. I'm not sure what this is from the sample data product, so it's not the final version. Then the other level 2 data product that I'm most familiar with, because I do deformation mapping, is the unwrap the interferograms. We're going to systematically unwrap the interferograms and geocode them, so they're going to be geocoded and unwrapped. And the data product will include actually both the original unwrapped interferogram and the wrapped. I mean, the original wrapped interferometric phase plus the unwrapped version. It's going to have an 80-meter spacing, and it'll also include the coherence magnitude and an estimate of this ionospheric phase delay that's estimated from those two bands that I mentioned earlier.
And Eric, there are a couple questions about the GunW product in the QA. So one from Drew Rotherham, with regards to the GunW products, can you comment on the unwrapping algorithm used and its expected performance in terms of unwrapping errors?
Yes, the ICE3 unwrapping algorithm is a new algorithm it's somewhat similar to SNAFU, but it's been improved to be something more like the two-stage unwrapper that we used to have in ICE2. It's ICE3 algorithm. I don't know the details of how it actually operates or what the performance is going to be, but we obviously hope that it's going to be at least as good as SNAFU. It was I don't know the details, but that's something we're going to have to see when it's actually getting real data. Was there the question?
The other question is with what temporal baselines will be available for the interferometric products, the GunW, the RIFG, and the RUNW.
Yes. So the NISAR mission is only going to be processing the adjacent in time pairs. So it's going to be processing the 12-day pairs. There was some discussion earlier about doing additional pairs, but we're only going to be systematically processing the 12-day pairs as a basic minimal interferometric data set. And there has been discussion about adding an on-demand system to process additional pairs. That's still under discussion, but the mission has been funded to systematically process all the 12-day pairs for all the interferograms. I can't see the Q&A while I'm doing the showing the screen.
I think you're caught up at this point.
Okay.
With questions.
So yeah, so the GunW file name has to have additional information. Obviously, it says GunW. It has the frame number. It has the information about the bandwidth of the data used, the polarization information. In this case, it's a single polarization HH. And then it gives the start time and end time of the reference SLC and the start time and the end time of the secondary SLC. So those are the two scenes that were used to make that pair. And then the rest of the file name is very similar to the other ones with the processing system version numbers, P for partial frame. All these ALOS data products are partial frame because they're much smaller than the full NISAR frame. M for medium orbit accuracy, process to JPL. There's also going to be special interferometry products only over the cryosphere region. These will be systematically processed over the major ice sheets of Greenland, Antarctica, and other major ice sheets such as the Patagonian ice field. And those will include the pixel offset tracking, the offset products, both in radar coordinates, ROFF and geocoded versions, GOFF, because some of the a lot of that cryosphere data is going to be acquired with the 80 megahertz mode that enhances the estimation of the offsets. There's going to be the RIFG, which is the radar coordinates and interferogram wrapped. That's at a higher resolution, so it hasn't been and not filtered to allow additional processing by the user, and a radar coordinates unwrapped interferogram. The cryosphere team wanted to have these interferograms and radar coordinates because the topography in the cryosphere regions is changing so rapidly in some cases that they wanted to be able to use a different DEM for the geocoding if they needed to. So these will only be processed over the cryosphere regions systematically. But of course, the software is available if people want to run this for other places. So these data products are going to be large. The size of the data products is going to depend on the range resolution. There are some places over sea ice where they're only going to acquire the 5 megahertz data. That's 20 meter resolution. So those will be much smaller, but most of the Earth is going to be covered by this 20 plus 5 megahertz mode. So the RSLC will be about 13 gigabytes, GSLC 11 gigabytes. The 40 megahertz SLCs have twice the amount of data, so they're twice the size. One of the other things about the 80 megahertz mode is that it's half the width. It's not 240 kilometers wide, it's only 120 kilometers wide. So even though it has, and it's only single polarization, so The SLC size is actually smaller because it's half the width and only one polarization. G-coves will be produced at 80 megahertz. I'm not sure. Most of those will be 3 GB size. Again, they're going to have different sizes based on the input data. If it's acquired at high spatial resolution, it's going to be twice size. The geocoded unwrapped interferograms have the same size because they're always going to be produced at the 80 megahertz, 80 meter pixel spacing, whereas the G-cove will have 80 meters at the when it's acquired at 20 megahertz, but 40 meters at when it's acquired at 40 megahertz. And these special ice products are somewhat smaller because they're the geocoded offsets. Those are the sizes of the other data sets. Again, these are the geocoded offsets are done at the same spacing, no matter what the input data set size is. And the final version of the soil moisture has not yet been determined. So the sample data products are all online. The ICE3 software is stable and the launch version is going to be delivered very soon. You can get the full ICE3 software at GitHub on GitHub. The sample products are very close to the final specification, so develop these to enable people to start using them for downstream workflow development. We're doing some simulated data that has the full NISAR frame size, and those will be released later this month or early next month to enable people to use workflows that have the full data size. But the first sample data products are based on these ALOS data products that are about 1/20th of the full NISAR frame. So there's some additional slides here that give more details on the mode specifications. I'm not really an expert on all the different modes. I'm gonna skip over this and leave these as slides available for future reference. And the level, as I mentioned earlier, the level 0 data will not be provided on frame by frame basis, but on these long data set, data acquisition, data take files. That's just additional information about the GunWs. There's also this product versioning information that's going to be included in the file names and in the metadata. It gives information about the software version, the ICE3 version, the specification of the product. If we change the product data format, there'll be a change to that number. The version of the product specification version, and any change to the quality, like there'll be a initial preliminary not fully calibrated products have lower version numbers, and then later that version will be bumped up once with the data is fully calibrated. And then there's an additional number that tells about all the other software processing configuration to have full provenance information. So I think that's it for all the. It's a lot of information here. It's a very complex system. other satellites have not been producing so many different data products. It's a little bit, it's a much more complicated data system, and but it's going to be worth it because it's going to be a lot of extremely helpful data. Thanks.
Thanks,
Are
Eric.
there any more questions?
Oh, actually, it does look like there's one more in the QA. Does the G cove contain only intensity channels?
Yes, the G cove is is the amplitude of the polarizations and the covariance of the channels. For detailed analysis of the polarization, people often look at the covariance of the different polarizations. That's why it's called G cove and not just radar terrain corrected amplitude. It's an amplitude only product, and it has been multi-looked.